First of all, I would like to thank the organizers for the very kind invitation. I'm really happy to give this talk. And this is a joint work with my student, Subo Kudeku, who is actually currently in the audience, and he will give another talk on Friday morning. So we have been actually working on this project for almost maybe 3 years, and Subo has done the majority of the work, so he is actually more qualified to give the talk. So the motivation of this project comes from a very standard practice that statisticians want to analyze a collection of z-scores. And for example, here for z-score, each xj is either associated with a null distribution or alternative. And the goal is to conduct standard multiple testing procedure to discover those samples associated with that alternative while controlling type 1 errors such as family-wise error rate or false statistical rate, right? And one of the standard assumptions that people put is that the null distribution is always assumed to be known. And here for z-score, it is typically assumed that it is exactly normal 0, 1. And you can use that to transform the z-score into p-values to do multiple testing. However, such assumptions have been challenged by statisticians, especially by a series of Efron's paper that he observed that in many gene expression data, when you actually plot the gene expression data as a histogram, it does not really fit the theoretical null distribution of normal 0, 1, which is given by this green curve as you can see in these two pictures. So more flexible assumption of null distribution is needed. And there are several reasons for the failure of null distribution of normal 0, 1. And among all the other reasons, Efron has discussed correlation among z-scores and unobserved covariates. And I will later talk about why correlation may lead to the failure of the theoretical null. But to address this issue, Efron suggests the following two-group models. In order to assume that the null distribution is non-normal 0, 1, you actually want to keep the location and the variance parameter to be flexible. So you don't assume it's normal 0, 1. Instead, you assume it has a general location parameter theta and a variance parameter sigma square. And these parameters are not known. You are supposed to learn these parameters from the data. Well, you may be wondering, is this actually possible? Well, the key observation here is that in the typical large-scale inference setting, there are usually much more samples that are associated with the null compared to those associated with alternatives. So for those samples that are associated with the alternative that has a different location parameter, these can just be treated as outliers. So this is a typical robust estimation problem that we are going to take this perspective, okay? So let me just use this slide to tell you why correlation may lead to the failure of a typical normal 0, 1 null distribution. So consider perhaps one of the simplest covariance structure. This is the one-factor model, or also known as the Rencontres correlation model. Here the z-score xj is written as the location parameter eta j plus noise. The noise has two components. The first component is shared across all the samples. The second component is RID, independent for all samples. And here, the random variables w and zj, they are just the normal 0, 1. And because of the shared component, you have correlation across all the samples. And in fact, if you compute the covariance matrix, all the off-diagonal entries of the covariance is exactly rho, meaning it's actually a equicorrelation structure. So this, even for this very simple covariance structure, you can already see something very interesting. If you write down the marginal distribution of the null distribution, it is actually still normal 0, 1. But when you do the histogram plot of the z-scores, what actually governs the behavior of the histogram plot is not the marginal distribution, but the conditional distribution given the common variability W, right? The conditional distribution, because of the correlation, is no longer normal 0, 1, but has a non-zero location shift and a different variance from 1. And because you do not know the correlation strength rho, you do not observe the random variable W, you have to estimate these location and variance parameter from the data, okay? And this is our goal. We are trying to understand the optimal estimation of the null distribution in the presence of the outliers, which are from the alternative group, okay? And I want to put the Efron's two-group model in a robust perspective to compare with other robust framework that we have seen in the literature. But first, let me try to write down a Bayesian formulation of Efron's two-group model, so the comparison is more clear. So what I'm going to do is to put a prior distribution on each sample, whether it's from the null distribution or from the alternative groups, right? So for each j with probability 1 minus epsilon, it's from the null, with epsilon, it's from the alternative. I'm also going to put a prior distribution on the non-null effect eta j. So when eta j is sampled from some prior distribution q, then the alternative distribution is going to be a convolution between Gaussian 0, sigma square, and q. Okay? And in today's talk, we are going to mainly focus on the frequencies formulation of Efron's model. But I want to mention that all the results are also going to hold under the Bayesian formulation, and these two different formulations are more or less equivalent to each other. And in the robust estimation literature, probably the most popular model people have considered, and definitely in the last talk, is Huber's contamination model. Just like Efron's setting, in the Huber setting, you also have two groups, the group inlier corresponding to the null distribution, the group of outlier corresponding to the alternative distribution. The main difference is that in the Huber setting, if the sample is from outlier, it's no longer distributed according to a Gaussian. Instead, it can be an arbitrary number, which is denoted by this delta measure at location eta j. Okay? You can also write down a Bayesian version of the Huber's model, which is this mixture distribution by putting a prior on eta. Okay? And the comparison between the two Bayesian versions is very clear that Huber's model is much more general, because the contamination distribution in the Huber setting is an arbitrary distribution Q, whereas in Efron setting, it has to be in the form of convolution between a Gaussian and a Q. Okay? So if you are familiar with the results in the literature on Huber's model, you should expect better results should be obtained under Efron's two-group model. So let me first review what we have already known in the literature in the Huber setting. So in the Huber setting, suppose you generate samples or z-scores xj from Huber's contamination model, whether it's from the frequencies formulation or the Bayesian version, it does not really matter. I'm going to denote the number of outliers by k, and epsilon is called the contamination proportion. It's the same epsilon that we see in Ashok's talk, epsilon equals k over n. Then we know that the minimax rate of estimating theta with respect to the square error loss has this function. It has two parts, 1 over n, the parametric rate, and then k squared over n squared. That's the effect of the contamination. Okay? And so one takeaway I want to emphasize is that in the setting where epsilon or k over n is a constant, which means the contamination proportion does not go to 0 as n goes to infinity, then the minimax rate will also be a constant, which means consistency cannot be achieved. Right? This is quite a disappointing message that we get from the results for Huber's model, that for a constant level of contamination proportion, you cannot achieve consistency. And the reason why consistency is impossible in the Huber's model can be illustrated by the non-identifiability of the parameter. So here I'm trying to illustrate this point by looking at this example where epsilon equals 1 over 10. Okay? And the reason theta is not identifiable is for this mixture distribution in the Huber setting, you can find a different pair of theta tilde and q tilde such that the same distribution can be represented in the same form by using the different pair of theta tilde and q tilde. However, you cannot do that in the Efron setting because of the additional convolution structure with a Gaussian distribution. In the Efron setting, the parameters theta is actually identifiable. And to see why is this the case, I'm trying to rearrange the mixture distribution as a convolution between what's inside the parenthesis and the Gaussian normal 0 sigma square. Right? So as long as we can show theta is identifiable in the parenthesis, then after convolution, it's still going to be identifiable. And this is actually quite obvious. So suppose you generate a random variable from the distribution inside the parenthesis, then by definition, at least 90% of the chance it's going to take exactly the value of theta, meaning that theta can be actually defined as the mode of this distribution in the parenthesis. That's how it's defined, it's identifiable. So the message here I want to make is that the null distribution should be able to be consistently estimated even if the non-null proportion or the contamination proportion is a constant level. Okay? And that's the key difference between Efron and Huber's setting. So what is our goal? Our goal today is to understand the minimax rate of estimating the null parameters theta and sigma squared under Efron's two-group model. So here I'm just rewriting Efron's two-group model in this Gaussian sequence model representation. So our observation xj can be decomposed as theta, that's the parameter that we want to estimate, plus gamma plus Gaussian noise. So here the vector gamma is called the contamination vector. If gamma j is 0, that means there is no contamination or it belongs to a null group. Otherwise, it's going to be from the alternative group. Okay? And the L0 norm of the gamma is controlled by k, so k bounds the number of outliers, or k is the largest number of non-null samples. Okay? So this is the question that we want to solve. So before telling you the main results, let me first try to briefly review what people have been doing in the literature. There are mainly two types of ideas. The first line of idea is based on penalized estimation. This is fairly straightforward. You first write down the least square objective, and then since the contamination vector gamma is sparse, it is very natural to put an L1 penalty to encourage sparsity. And this is just a very easy convex optimization problem that you can solve. For example, if you first optimize over gamma, then when you optimize over theta, it is exactly equivalent to optimizing the Huber loss. And Huber loss, if you remember Huber loss, is the definition that is an interpolation between the least square loss and the least absolute deviation loss. It is probably the most popular method that people are still using in robust statistics. And this very nice equivalence between the two methods has been observed back in 2007 by Ganas and Antoniades, and later Yuan Shi and Art Owen in 2011 also discussed equivalence for other general penalty functions. And in terms of the theoretical justification, back in 2019, Collier and Daladian proved that the minimizer of this penalized estimation satisfies this rate. Again, you have 1 over n. That is the first term. The second term is k squared over n squared times log n. So here, for now, just to ignore this extra log n factor, then this will be exactly the same rate as the minimax rate of Huber's model, right? So in particular, when k over n is a constant, this rate does not go to 0, so you don't achieve consistency. So even though penalized estimation is appealing, it's equivalent to minimizing Huber's loss, it does not really take advantage of the additional convolution structure in Efron's setting, so consistency cannot be achieved. With the second line of research, try to extract information of null distribution from analyzing the characteristic function. So here, I'm writing down the empirical characteristic function. I want to convince you why characteristic function is a nice idea to study for the following two reasons. The first reason is that the characteristic function, by definition, is supposed to contain all information of the corresponding distribution. So by using the characteristic function, you're not going to lose any information that you want to extract. Okay? And the second reason, the second reason is that if you look at the definition, characteristic function is the average of bounded function. Right? Each term that you average over has norm exactly 1 by definition, so it is actually robust. Even if one of the contamination vector, gamma j, becomes arbitrarily large, it will not change the characteristic function to an arbitrarily large value. Okay? So characteristic function is naturally a robust quantity to look at. It is very suitable for robust estimation. So let's try to take expectation of this guy to look at the population version and to see where the information is. So here, I'm trying to organize everything about the location parameter inside the bracket. Okay, so just ignore everything outside the bracket. So inside bracket, you have two terms. The first term that receives the weight 1 minus k over n has information about theta, right? And the second term that receives the weight k over n contains information of the outlier structure. And the function q hat is defined here. It is actually the empirical characteristic function of the contamination vector theta plus gamma j. Okay? You really wish the q hat is not there, so this is only a function of theta, then you can define estimated theta hat from manipulating this characteristic function. However, theta hat is there, so what you do, well, people have been doing in the literature is the following strategy. So they put assumption, under such assumption, the assumption says q hat of t goes to 0 as t goes to infinity, okay? So under this assumption, you can just take a frequency value t to be sufficiently large so that the effect of q hat of t is negligible. And as long as this approximation roughly holds, you can expect to manipulating the characteristic function and get an estimator for theta. Okay? And this is actually exactly what was done by Tony Ka and Jiaxun Jing back in 2010. And their estimator is able to achieve this rate, 1 over n plus k squared over n squared, divided by this logarithmic factor. Okay? So here, the exponent on the log corresponds to the decay rate of q hat as t goes to infinity. Okay? And because of this additional logarithmic factor in the denominator, now if k over n, the contamination proportion, remains a constant, it is still consistent. The error goes to 0. Okay? However, you can only obtain this result under the assumption that q hat can be ignored for large t. Is this assumption reasonable? Well, personally, I don't think it's reasonable for the following 2 reasons. The first reason is that if you read the paper, then you will soon convince yourself that the assumption that q hat goes to 0 as t goes to infinity actually implies all the contamination vector values, gamma j, to be uniformly bounded. Okay? This is actually not as satisfying considering you are actually solving a robust estimation problem. You actually want a robust estimator to be able to handle arbitrary large outliers. And in particular, the reason that you want to use the cursive function is that cursive function is able to deal with arbitrary large outliers. Now you put assumptions so that the gamma j's are bounded, it actually defeats the original purpose of using the cursive function. Okay? And the second reason is kind of strange. If you look at the paper by Tony Ka and Jiaxun Jing, not only they achieve consistency when k over n is a constant, consistency still holds even when k over n is above the level of 1 over 2. Okay? So this saying that even if you have more outliers than inliers, you can still achieve consistency. But obviously, when k over n is above 1 over 2, the estimation of theta is not possible because theta is no longer identifiable. Right? And the only reason you can still achieve consistency is just because of the extra assumption that you put on q. Okay? So in today's talk, we are going to see how we can remove every assumption on gamma. Can we actually derive the minimax rate without any assumption on the contamination structure? Okay? So even though I think the cursive function is a nice idea to look at, the way they manipulate the cursive function, I don't think it's correct. There's a question.
Yeah, I have a couple questions. The first one is, so when you're assuming this, so there's a difference between the Bayesian and frequencies perspective, right? Because when you have the Bayesian, you're implicitly assuming that your eta j's are sampled ID from the same distribution.
Yeah.
So this cannot work at all without this, right?
So this derivation actually works under the frequentist formulation, but then under the Bayesian...
What is Q in that case? I'm a bit confused.
I define Q here, so let me show you the definition. This is the Q. So in the frequency formulation, it's just the average. In the Bayesian formulation, it will be an integral.
Okay. And so also the other thing is, so I'm trying to see if the only hurdle is the fact that, so you said one of the issues with this assumption that it goes to 0 as it goes to infinity is that it implies that this gamma j's are bounded. But if the gamma j's are unbounded, you can always do some like pre-cleaning step, right? Since you have Gaussians.
Yeah, you can do that, but I think that will give you some additional logarithmic factor because the way you do that is usually based on the largest value of Gaussian observations.
How does to be fair on that? I mean, if you are assuming the Bayesian formulation,
yes,
if Q just has a density,
right,
whatever,
yeah,
then you have that Riemann-Lebesgue lemma that the Fourier transform to 0.
Yeah,
you don't need any boundedness at all.
Yeah, I agree. So
condition in the frequentist formulation, but it's by no means necessary.
I agree. So I think what you are saying is if Q has a density and the density is independent of the sample size, then you don't need any assumption. This is true. But actually, what we want is a non-asymptotic result. We want the minimax result to hold for any value of the sample size n. So in the worst case, Q and gamma, they can depend on n, and in that case, it will fail.
No, but in any case, then also this tail behavior of the characteristic function of Q is just something on the regularity of the density.
Right.
It's nothing about robustness. It's not about the moments.
Yeah.
So you could formulate that even kind of non-asymptotically.
Yeah.
In a Bayesian framework.
Yeah.
I agree on the frequentist, it depends.
Yeah. I don't think there's much difference between frequentist formulation, Bayesian formulation.
There's no robustness issue. It's a regularity how the gamma j's are drawn.
Yeah, it depends on, at the end of the day, I think it depends on how you're manipulating the Curtis function. What they did is to take derivative with respect to t, so you can see that theta may come down, right? But as theta come down, the theta plus gamma j will also come down. That's why they need the boundaries of these quantities. So if you have a way to deal with Curtis function in a better way, as we will show later, then probably all of these assumptions can be removed. Any other questions? Okay, great. So let me show you our results. So we want to consider Efron's two-group model, and the only assumption that we put is gamma is sparse, and it may not be that sparse because k can be large, right? There is no additional assumption, and we showed that the minimax rate for estimating theta, which is a function of k and n, has this formula. It has 4 different regimes. So in the beginning, it has the parametric rate 1 over n, and the first phase transition boundary is root n. So after root n, it's going to be a non-parametric rate. The non-parametric rate scales as k squared over n squared divided by a logarithmic factor, and because of this additional logarithmic factor, you are able to achieve consistency even if k over n is a constant. And then starting from here, you have a different phase transition boundary, which happens at k equals n over 2 minus root n. This is actually the consistency boundary, below which it is consistent, above which it is not consistent. Okay. I actually also want to mention that there is independent work going on by Alex Carpentier and Luca. They are working on exactly the same problem, and they are also able to derive the minimax rates, at least in the first 2 regimes. So definitely we are not the only group who are working on this problem. Okay, so let me give you some interpretation of the results. In the first regime, it says that when the number of outliers is below the level of root n, you achieve parametric rate. And for the second, if you look at the second regime, it tells you that even if k of n, which is the contamination proportion, is a constant, consistency can still be achieved. In fact, whether or not k of n is 1 over 100 or 0.49, it doesn't really matter. The minimax rate will be specialized to 1 over log n, right? It goes to, still goes to 0. And then if you look at the third regime, it's kind of clear that when k takes the phase transition boundary, when k equals n over 2 minus root n, then this ratio inside the log is going to be constant. So the minimax rate will be constant. So as long as k is below this phase transition boundary, you get consistency, above which you cannot get the consistency. So from the third regime, you can actually derive the necessary and sufficient condition for consistency, which is this condition. It says that whenever the difference of the size of the null and the alternative is of larger order than root n, then you can achieve consistency. Otherwise, you couldn't. Okay? And in the last regime, not only you cannot achieve consistency, the minimax rate actually goes to infinity at the rate of logarithmic factor of sample size. And in most cases, it's just log n. All right, so having told you the minimax rate, let's try to discuss what kind of procedure that we can use to achieve the minimax rate. And as I just said, we are trying to use the Curtis function as well, but in a different way. So I want to actually mention that the main challenge of the Curtis function lies in the term that I called in red. This is the contamination structure. You really wish that this term is not there. So everything that is difficult is how to handle this term. But for this point, let's just assume the red function is known. Let's suppose you know gamma. Then how do you extract information about theta? Okay. So the first thing I'm doing is to move the first term in the product exponential it theta minus t squared over 2 from right to the left. So the equation becomes cleaner. Okay. And then I can set up the following optimization problem. So the question is, for which value of mu does the left-hand side of the equation equals the right-hand side of the equation? Okay? And clearly theta will be a minimizer because if you plug in mu equals theta, the difference will be exactly 0 because of the previous equation. The question is whether theta is the unique minimizer or not. Right? So theta is not a unique minimizer because if theta is a minimizer, so is theta plus 2 pi over t, theta plus 4 pi over t, because the Curtis function is periodic. It's just a sines of sines cosines. Okay? And to overcome this issue, you cannot just use one frequency value of t. You have to use all frequency values. So if you try to solve the minimization optimization problem uniformly over all frequency values t, and this will give you the unique minimizer definition of theta. Okay. However, this is true only by assuming that the red function is known. What if the red function is not known? Well, one strategy is if you do not know the contamination vector gamma, you can just fit it. Okay? As we see from the previous slides, one strategy is to use penalized estimation by putting an L1 function and then fit the gamma. However, notice that the gamma is actually a high-dimensional object. If you do that, you probably will have some cost, which will result in suboptimal rate. Right? And the advantage that we have in the frequency domain is that you do not have to actually fit the high-dimensional vector gamma. Notice this red function is just a one-dimensional complex number. So we are going to just fit this one-dimensional complex number. And by triangle inequality, we know this red function has norm at most 1, and that's the regime that we are going to fit this function. It's just a one-dimensional complex number to fit. And the other subtlety is that when you do minimization of this zeta, it's important to put this guy inside the soup so that the proof works. Okay? And we prove that if k of n is strictly below 1/2, this optimization problem exactly gives you the unique minimizer, which is theta. This can also be regarded as a definition of theta just from characteristic function. It does not use any assumption or any knowledge on a contamination structure gamma. Okay? So now we have obtained a definition of theta using the characteristic function. So to introduce an estimator, we just throw away the expectation operator. This will give you a sample version which you use as theta hat. Okay? So another difference between the sample version and the population version is that in the sample version, we have to truncate the frequency. Notice that we do not take soup over all t in R. Instead, we only take soup on an interval from -tau to tau. Why do I need to do that? Well, in order that theta is a good estimator of theta hat is a good estimator of theta, you need concentration between average to its expectation. However, if you look at this average function, this function has t²/2 in the exponent. So if you calculate the variance is actually an exponential function in terms of t as t goes to infinity. So if you do not put the truncation on the frequency level, the variance will simply be infinite. There is no concentration, so this truncation is actually necessary. As a cost of truncation, you have to incur additional bias, which is of order k over n of tau. Okay? And then you can also compute the stochastic error. This is just 1/√n times the standard deviation. It's very easy to calculate. Of course, you have to use some empirical process theory to make sure this concentration is uniform, but that's just a standard practice. So in the end, if you put together the bias and the stochastic error, you can choose tau so that these two terms are balanced. It turns out this choice is going to do the job, and that leads to the minimax optimal estimator that achieves the optimal rate, at least when k is below the consistent threshold n/2 minus √10. Okay? So somehow this Fourier-based estimator only works when k is below the level of n/2 minus √10. When k is above this level, we have the inconsistent regime. This estimator no longer works. However, a different estimator, which is actually simpler, continues to work in the inconsistent regime. So let me tell you what it is. So this is extremely easy to define. So first of all, you try to find an interval. The interval is from mu minus h to mu plus h. So it is an interval centering around mu and with bandwidth h. Okay? Then you try to move the value of h, so you slide the window across the real line until the window collects as many data as possible. Okay? And the output of the location is going to be theta hat. And this estimator is actually known as the kernel mode estimator because you can rearrange the formula so that theta hat is the maximizer of a kernel density estimator. Okay? The kernel mode estimator has a very long history. It actually goes back to the original paper by Emmanuel Parson back in the 1960s when he proposed the kernel density estimator. He also proposed in the same paper that you can also use the maximizer of the density estimator to estimate the mode. And later, Bill Eddy in the 80s studied the asymptotic property of the kernel density estimator. And actually, Efron in his 2004 work also used a mode estimator to estimate the now parameter theta of the now distribution. Of course, he didn't use the kernel density estimator. Instead, he used Poisson regression to estimate density and then output the maximizer of the density estimator as an estimator for theta. Okay, so here we are actually doing something similar. So we are able to show that if you choose the bandwidth parameter as this form, then it achieves the minimax rate in the inconsistent regime. Okay, I actually want to highlight here the choice of bandwidth is not standard. It's actually widening instead of shrinking because, as you can see, as n goes to infinity, the bandwidths actually diverge. Okay, so in fact, the analysis of this kernel mode estimator is completely different from what has been done in literature. So what has been done in the literature is always the two-step procedure. You first prove the closeness between the density estimator and the density, and then you prove the two argmax are close. However, if you choose a widening bandwidth, which is necessary for this problem, the corresponding density estimator will be a disaster. It's going to be a suboptimal, highly suboptimal density estimator. Nonetheless, the mode estimator is still minimax optimal. Okay? All right. So if I still have time, I can briefly discuss how we prove the lower bound. The lower bound relies on a standard hypothesis testing argument that we are trying to formulate two hypotheses, one associated with the location 0, the other associated with theta, and then we try to construct distributions Q0, Q1, such that the corresponding marginals P0, P1 cannot be distinguished in the sense that chi-square divergence is bounded by the level of 1 over n. Okay? We are trying to find the largest possible theta such that this construction is possible, and then this theta will be our minimax lower bound. So our construction is based on two ideas. The first idea is kind of trivial, is when epsilon is exactly 1 over 2, you can just take this simple delta point construction. So Q0 is a delta measure at theta, Q1 is a delta measure at 0, and then because the symmetry by 1 over 2, the role of contamination, the role of inlier and outlier is switched, so you get exact match between P1 and P0, right? No matter how large theta it is, you can always do this construction, which actually proves that the minimax lower bound is infinite, because when epsilon is 1 over 2, the problem is not identifiable, okay? Probably this construction continues to work when epsilon is very close to 1 over 2, but when epsilon is small, this does not work. We actually need a better construction. So the better idea is based on Fourier, based on matching the Fourier domain. So we first have this inequality that says if you can match the two distributions in the Fourier domain in the sense that the derivatives of Fourier transform are close, then the chi-square divergence between P0 and P1 is also going to be small. Okay? And this inequality is sort of standard. You can find it in many papers in the literature. So inspired by this inequality, what we are trying to do is to first write down the Fourier transform of the two distributions. And here, we are trying to find Q0 and Q hat so that these two Fourier transforms are as close to each other as possible. Yes, please.
Chao, does it work? Is this the standard bound in terms of moments? Equivalent to that?
Yeah, it's very similar. If you do moments, you also have a similar bound, and then we know that the derivative of the Fourier transform has relation to moments as 0, so it's kind of in the same spirit.
I think it's exactly the same.
Yeah, I think so too. I agree. Yeah, you're right. Okay, so if you just set up this identity so that P0 hat equals P1 hat, then the requirement on Q is that the difference between the Fourier transform for Q1 and Q0 needs to satisfy this equation. Okay? You hope this is true for all values of frequency t, but obviously this will be impossible because what's on the right-hand side can be large when epsilon is small, what's on the left-hand side by definition is bounded. Okay? So this is impossible. You cannot hope this equation to hold for all values of t, but what you can actually prove is at least you can find constructions so that this match holds for t whose absolute value is bounded by tau. So you can actually do exact match from negative tau to tau. And when t is above the level of 2 tau, you just give up. Okay? You just set the difference to be 0, meaning you don't do anything. And for technical reason, between tau and 2 tau, it's a gradual tapering from non-zero to 0. So we prove as long as theta is chosen as the order of epsilon over tau, this construction is possible. Okay? Well, is this construction good enough for us to solve the problem? Well, sort of. It sort of works when epsilon is small, but it does not work when epsilon is close to 1 over 2 because, as I said, when epsilon is close to 1 over 2, you should expect that you get exact match. right? This bound is obviously non-zero when epsilon is 1/2. Okay? So what construction work when epsilon equals 1/2? Well, we just mentioned that previously discussed a trivial construction of delta measures is going to work. So our idea is just to combine the Fourier method with the delta construction by a simple linear combination in the Fourier domain. As long as you choose the weight correctly, you are able to show the following result, that here we have a better result in terms of matching in Fourier domain, that not only can you do exact match when t is small, but when t is large, you actually do approximate match, right? So this guy is non-zero. It's much better than zero. Zero meaning you do not do anything, okay? Now with the coefficient to epsilon, it's actually approximate match, right? Notice when epsilon is 1/2, 2 epsilon is 1. And for this factor, 1 minus epsilon over epsilon is also 1 when epsilon is 1/2. So the closer epsilon is to 1/2, the more accurate this match is going to be, okay? With this improvement, you can show that the chi-square bound has this additional 1 minus 2 epsilon factor in front of it, okay? So what you need is the chi-square to be bounded by 1/n, and if you solve that requirement, this will give you the choice of the bandwidth, choice of the frequency value tau, which is of this form, okay? So if you still remember the choice of the frequency value in the upper bound construction, this is exactly the same frequency that you use in the lower bound. It's very satisfying to see the same frequency that you choose, meaning that the information is really from negative tau to tau for this construction, okay?
Sorry, remind me of what tau is in the lower bound?
The tau in the lower bound is the point where you exact match the two distribution in the Fourier domain. Okay? So above 2 tau, you just do approximate match, because the exact match for all t is impossible. Any other question? How many minutes do I still have? 2? Okay, thank you. All right, so let me quickly talk about the variance estimation. So previously we just assumed the variance is known. So let's talk about variance estimation. It turns out it is also based on a cursor function, but this time we are going to take the norm. And let's take a look at the population version of this n hat. It is this formula. If you look at the first factor, it's exponential it theta. It immediately goes away because you take norm, right? So this first factor has norm 1. So by taking norm, you just profile out the nuisance parameter theta. You do not care. You care about a variance estimation, okay? And then the information of theta, the information about the variance parameter is in the first term. So what you can do is to first take log and then divide by t squared over 2. If you do that, you end up with this equation, which means you can use -2 log n of t divided by t squared to estimate sigma squared, despite the additional bias term, okay? So this is the estimate that you can use if you are able to tolerate this bias. And in fact, this is exactly the estimator proposed by Kumon, Correa, and Dao and Tsipakov back in 2021. And how do you choose t? Well, you want to choose t to be sufficiently large so this bias is as small as possible. However, the larger the t you choose, the worse the concentration between n hat and n. Okay, so in the end, the choice of t is going to be a matter of bias variance trade-off. Okay? However, the result of Kumon, Correa, and Tsipakov needs to assume that the k of n is sufficiently small, if I remember correctly, it needs to be smaller than 1/8 in order this estimator works. Okay? What if k of n is large, say 1/3, or even better, close to 1/2? It turns out we need some modifications so that this estimator continues to work when k of n is close to 1/2. So in order to motivate this modification, let me try to give you a better understanding of the bias. So what's going on in this bias? The most complicated term is the term in the parentheses, right? So I'm just taking this term over there to highlight its analysis. I'm going to put a norm and then square it. So this is just a direct calculation. And then I'm going to bound the first 2 terms by 2, right? So you get this bound. Now, how do you bound this average of cosine? Well, average of cosine, a trivial bound is it's greater than -1. Okay, so 1 minus -1 is at most 2. Multiplied by 2 is at most 4, right? So if you square it, this is at most 4. Before squaring it, the term in the bracket, the term in the parentheses is at most 2. right? So you hit the 2 by k over n, you want 2k of n to be bounded away from 1, otherwise the bias is going to blow up. That's why you need k of n to be bounded below by 1 over 2. However, it turns out we have this sort of cute mathematical result that says that if you don't just use one frequency value, if you collectively use a collection of frequencies, then regardless of the structure of the contamination, there is always a frequency value t in the interval from tau to 10 tau, so that the average cosine is no longer bounded by a trivial -1, but a better -1 over 5 bound. If you use this bound, even if k over n is 1 over 2, it does not matter. The bias does not blow up, okay? So our modification of this estimator is just to take advantage of this fact by taking an extra optimization over the frequency value, and this allows us to obtain the result that which is minimax optimal in terms of variance summation all the way up to k equals n over 2, okay? And in the end, you can just combine the estimator for the theta and the sigma square so that you get a minimax optimal estimator for the null distribution, okay? I think I'm going to stop here. Thank you.